Students, in last lecture of thermal properties of matter, we learn some coefficients, that is alpha, beta and gamma. Alpha is coefficient of linear expansion, beta is coefficient of aerial or superficial expansion, and gamma is the coefficient of volume or cubical expansion. So briefly we studied it in our previous lecture, and here in today's lecture we are going to learn the relation between these three coefficients, that is alpha, beta and gamma. Here is some technical problem. Alpha, beta and gamma is not reflecting, so you try to understand. So we'll start to learn the relation between three coefficients, that is alpha, beta and gamma. So we'll start it. Now in this we'll try to consider a square plate. We know that in superficial or aerial expansion we consider a square plate, and length of the square plate is L naught, L0. Okay, and we know that when heat is supplied to the plate, the temperature is increases and it expands. This expansion is isothermal expansion because the square plate is equally expand in all the direction. Uh, Remember, L naught is its length, and definitely when it expand, the length becomes LT, means there is increase in length and temperature is increases, that is T degrees Celsius. Now in previous lecture we studied that the difference between the length, that is increase in length and original length, is change in length. Okay, and we studied the equation, that is change in length is equal to alpha L naught delta T. Here is again the problem, I am repeating. This question mark is alpha L naught delta T, capital T is here, this delta T is change in temperature. Now we will write this negative L naught is to the right hand side, so our equation becomes LT is equal to L naught plus alpha L naught delta T. In previous lecture these equations are proper equations, there is no question mark, but here is some technical problem. uh, I remind to you, in last lecture linear expansion, we'll explain this equation. This is the increase in length we can determine by using the equation, that is change in length is equal to alpha L naught delta T. Is it? Now from where the proper equations are there, no problem. Now L naught is common from here, so our equation becomes LT is equal to L naught into bracket 1 plus alpha T. Uh, this is the increase in length. Equation 1. Now uh, we know that the plate is expanded in all the direction, so definitely there is the increase in length, so you can determine the change in length. Here we have to consider the area of the plate. At 0 degree Celsius original area is uh, a naught, but plate is the square plate, therefore square of the length is area of the plate. Original length and its square, it gives us original area. After heating, the temperature increases, it expands at T degree Celsius, and area becomes AT. Definitely this AT is equal to LT square. LT square. So if we square this equation, equation 1, we'll write LT square is equal to L naught square into bracket 1 plus alpha t bracket square. Remember uh, the square of this equation, but LT square is 80, change in or increase in area. LT square is 80 and L naught square is A naught. So our equation becomes 80 is equal to L naught into bracket 1 plus alpha t square. But in superficial expansion, we learn that in superficial or aerial expansion, AT is equal to A naught into bracket 1 plus beta T. Students, here the request is a previous video or previous articles must be thorough. Then only you can follow this article. Uh, Here equation for superficial expansion or increase in area, it will be AT is equal to A naught into bracket 1 plus beta T. This equation we obtain by using the linear expansion, is it? And this is from superficial expansion. This is equation number 3. Now compare these two equations. Left hand sides are same, so right hand sides must be same. So we'll write from equation 2 and 3, left hand side is A naught into bracket 1 plus alpha t square is equal to A naught into bracket 1 plus beta t. Now if we this A naught cancels on both the side, and this is A plus B bracket square, so we'll write 1 plus 2 alpha t plus alpha square t square is equal to 1 plus beta t. Here alpha square t square, this term is neglected. Why it is neglected? Because alpha is very small. Practically alpha is the coefficient of linear expansion and it is 0.002. This is the value, and square of this again a small uh, quantity, so it is neglected. Alpha square t square from this equation is neglected, so equation becomes 1 plus 2 alpha t is equal to 1 plus beta t. Again the 1 is cancelled and we'll get 2 alpha t is equal to beta t. T cancels and equation will be beta is equal to 2 alpha. Now in next part, this is equation number 4, and next part again we have to consider the same, that is change in length, etc. But here we have to consider the volume expansion. Now instead of a square of this, we'll consider the cube of this equation, equation number 1. It becomes LT cube is equal to L naught cube bracket 1 plus alpha t cube bracket raised to 3. So equation is here. I repeat, now uh, there is the relation between alpha and gamma. This is relation between alpha and beta. Alpha is coefficient of linear expansion. Beta is coefficient of aerial or superficial expansion. Now this onwards there is the relation between alpha and gamma. Gamma is the coefficient of volume expansion. So the cube of equation 1 is this, but in cubical expansion, uh, instead cubical expansion, cube is the length of the cube, original length of the cube is L naught, and after heating it becomes LT, and cube of this will gives us the volume of the cube. This is the original volume of the cube, and this one is when heat is supplied, temperature is increases and cube is expand, that time the volume is Vt. So our equation becomes Vt is equal to V naught into bracket 1 plus alpha T bracket raised to cube. Then again, this is equation number 5. Volume expansion, we studied the volume expansion, and the equation is Vt is equal to V naught into bracket 1 plus gamma T. Equation number 6, compare these two equations, that is equation number 5 and equation number 6. We'll write uh, left hand sides are same, therefore uh, V naught into bracket 1 plus alpha T cube is equal to V naught into bracket 1 plus gamma T. V naught cancels, and cube of this bracket will be 1 plus 3 alpha T plus 3 alpha square T square plus alpha cube T cube. So already we studied the cube of, that is A plus B bracket cube, uh, the identity, and the expansion of the bracket is here. Uh, Again, the higher power terms of alpha is neglected because alpha is very small, and square it becomes again small. So these two terms are neglected, and 1 plus alpha 3 alpha T is equal to 1 plus gamma T. Again 1 is cancelled, and we'll write 3 alpha T is equal to gamma T. T cancels, and we'll write 3 alpha, gamma is equal to 3 alpha. Now remember here, uh, equation number 7, here we'll write alpha is equal to beta by 2, beta divided by 2, and here we'll write alpha is equal to gamma divided by 3. So alpha will be the common, and it same in this equation, equation number 4 and 7. I repeat, here we'll divide 2 to the beta, it becomes beta divided by 2 is equal to alpha, and here it becomes gamma divided by 3 is equal to alpha. So alpha is there on right hand side, so the new equation will write this one, is it, that is alpha is equal to beta by 2 is equal to gamma by 3. So this is the relation between alpha, beta, gamma, that is coefficient of linear expansion, coefficient of areal or superficial, and coefficient of volume or cubical expansion. I repeat, these constants are not reflected over here, is it? So relation between alpha, beta and gamma is the title. Okay, here is alpha capital T, again alpha capital T. Only the mistakes are there in this slide. Now the next part, next topic of the chapter is specific heat capacity, and the specific heat capacity means when heat is supplied to the body, the temperature is increases. This we already studied in the previous lecture. Definition of the specific heat capacity of the body is here. Specific heat capacity is defined as the amount of heat per unit mass absorbed or given out by the substance to change its temperature by 1 unit. Here 1 unit is 1 degree Kelvin or 1 degree Celsius. Remember, when the heat is supplied to the body, it is absorbed or given out. Sometimes the body absorb the uh, heat energy, temperature is increases, and sometimes the heat is given by the body, or it is um, it uh, uh, gives to the body. So temperature of the body is increases or decreases. This is the specific heat capacity of the body. So here we'll consider delta Q is the uh, amount of heat energy, and it requires to change the temperature of the substance, uh, and it is directly proportional to the mass of the substance and change in temperature of the substance. Delta Q is the amount of heat energy supplied to the body, and it is directly proportional to the mass of the substance and the temperature of the substance. Okay, change in temperature, that is delta T. So we'll write this delta Q in mathematical statement. Delta Q, amount of heat energy supplied to the body, is directly proportional to the mass of the substance, even it is directly proportional to the change in temperature. So on combining these two statements, we'll write delta Q is directly proportional to M into delta T. So proportionality sign is removed and the proportionality constant is there S. This S is the specific heat capacity of the body. Specific heat or specific heat capacity of the substance. And rearranging this equation, we can determine the specific heat capacity of the substance or specific heat capacity of the body, and it is S is equal to delta Q by M delta T. Rearrange this equation, we'll get uh, S is equal to delta Q by M into delta T. Delta Q is the amount of heat supplied to the substance, M is the mass of the substance, and delta T is the change in temperature. So specific heat capacity of the body also you can define as it is the heat supplied to the body per unit mass of the substance per unit change in temperature of the body. Okay, so here we'll consider mass of the body is 1 kilogram and change in temperature is 1 Celsius. Therefore, heat supplied is equal to specific heat capacity of the body, that is S is equal to delta Q, and the units are here. Specific heat capacity in SI unit, you can write joules per kilogram per degree Celsius or joules per kilogram per Kelvin. Okay, and in CGS units, you write ergs per unit gram Kelvin or ergs per grams degree Celsius. So this is the unit for the specific heat capacity of the body. This is a little bit different uh, uh, topics are here in this chapter, and we'll try to explain it. Then specific heat capacity of the gases. This is for the particular material or solid body. Now in terms of the specific heat capacity of the gases, uh, uh, we know that if there is the a little bit change in temperature uh, causes a considerable change in pressure as well as the volume of the gas. Means what? Whenever there is a small change in temperature, there is the uh, uh, change in pressure as well as volume of the gas. Okay, so two specific heats has to be considered over here, that is specific heat capacity at constant volume and specific heat capacity at constant pressure. Remember here, due to the change in temperature, pressure and volume of the gas is changes, but here we have to consider the specific heat capacity of the gas at constant volume and constant pressure. At constant volume is SV and at constant pressure it is SV. So simple definitions are here, we'll try to learn. So the first definition is principal specific heat of gas at constant volume, that is SV. Principal specific heat of a gas at constant volume is defined as the quantity of heat absorbed or released for rise or fall of temperature of unit mass of gas through 1 degree Kelvin or 1 degree Celsius when its volume is kept constant. Specific heat of gas at constant volume is uh, the quantity of heat absorbed or released for rise or fall of temperature of unit mass of a gas through 1 degree Kelvin or 1 degree Celsius when its volume is kept constant. Now, here you try to understand the same statement is there for principal specific heat at constant volume, constant pressure. Only the change in the few words is there. Okay, so one definition you memorize, no need to by heart this one, automatically you can write it. Principal specific heat of a gas at constant pressure is defined as the quantity of heat absorbed or released for rise or fall of temperature of unit mass of a gas through 1 degree Kelvin or 1 degree Celsius when its pressure is kept constant. Same statements are there. Instead of volume, you use word pressure. So this is the definitions for specific heat capacities of the gases. Now two more definitions are same, that is uh, molar specific heat. Now molar specific heat and specific heat, there is a simple difference. Instead of unit mass we have to write uh, mole of the substance, 1 mole of the substance. So we can write the definitions, it is very easy. Molar specific heat of a gas at constant volume, again this is CV, that one is SV. Molar specific heat of a gas at constant volume is defined as the quantity of absorbed or released, quantity of heat absorbed or released for rise or fall the temperature of 1 mole of gas through 1 degree Kelvin or 1 degree Celsius when its volume is kept constant. Students, here no need to confuse molar specific heat uh, at constant volume and specific heat at constant volume. Only the change is what, instead of 1 unit mass of gas, that in, instead of that we have to consider 1 mole of the gas. Only the change is this, all other words are same. So no need to confuse over here. Again same definition for constant pressure and the definition is here. So these four definitions are same, only the change in words. uh, Specific heat at constant volume SV, molar के लिए you consider CV. Same thing about the pressure. Okay, so what is the difference or relation between specific heat capacity and molar specific heat capacity? We'll write molar specific heat capacity is molecular weight into the principal specific heat capacity. Molecular weight will write with a constant, that is mu, and Sp is the specific heat capacity at constant pressure, and Cv the specific heat capacity of the substance, that is Sv, has to be considered. So equation is Cp is equal to mu into Sp and Cv is equal to mu into Sv. uh, Only the change is there, this one is molar specific heat and this one is specific heat capacity at a constant pressure. So here mu is the molecular weight of the gas. It will be different for the different gases. Okay. Heat equation, again heat received or given out Q is equal to mass into change in temperature into specific heat capacity. Already we studied this equation. uh, so heat equation is the mass into change in temperature into specific heat capacity of the substance. Okay, so we'll write Q is equal to m delta T into S. So molar specific heat, again, what is molar specific heat? Uh, if the amount of substance is specified in terms of mole instead of the mass, that is in kilogram, the specific heat is called molar specific heat. So this is the big difference between the specific heat and molar specific heat. So here by this equation you can convert the specific heat into uh, molar specific heat. Mu is the molecular weight of the substance. Okay, delta Q is the heat supplied and delta T is the change in temperature. So SI unit of molar specific heat capacity is um, joules per mole per degree Celsius or joules per mole per Kelvin. Now heat capacity definition: heat capacity or thermal capacity of the body is the quantity of heat needed to rise or lower the temperature of the whole body by 1 degree Celsius or 1 degree Kelvin. Remember students, here whatever the molar heat, specific heat or heat capacity of the body, it relates to the uh, change in temperature. When the temperature is changes, when heat is supplied to the body, the temperature is changes. So what kind of heat is required to rise or lower the temperature of the body is the heat capacity of the body. Very simple statements are here, very simple definitions are over here. So we'll try to understand it. So heat received or given out, it is mass. Uh, this temperature is change in temperature is 1 and specific heat capacity of the body, that is S. So we'll write M into S. Heat received or given out is equal to mass into specific heat capacity of the body. Now the next article is calorimetry. This is the measurement technique of the exchange of heat. Okay, calorimeter is an the experimental technique for the quantitative measurement of the heat exchange. What quantity of the heat is exchanged, that you can measure by the science, that science is uh, known as the calorimeter. ठीक है? Now in this chapter we'll try to learn what is the calorimeter, and in the last topic of this chapter we have to consider the calorimeter uh, to learn the Newton's law of cooling. Okay, so device in which heat measurement can be made is called calorimeter, or device which used to measure the heat for measurement of heat is called calorimeter. Whatever the words you want to use to define this calorimeter, you can use it. And the diagram. Okay, this is the container, wooden container, and a cylindrical vessel is there inside the box, wooden box, and lid is there having two holes. In one hole thermometer is inserted and another hole the stirrer is used. Okay, there is the gap between the cylindrical pot and the wooden uh, jacket. Okay, this gap is filled with the insulator, heat insulator. Okay, either air, wool, sawdust is used. So this is the basic diagram of calorimeter. There may be the question, draw neat label diagram of calorimeter for 2 marks. So we have to draw the diagram and uh, give the names to the parts of calorimeter. Now explanation is very simple. It consists a cylindrical vessel and stirrer, as well as lead of some material like copper or aluminum. This is wooden frame is there as a lead in our laboratory. Then this one is, just I said, this cylindrical vessel is in a wooden jacket, and insulating material like glass, wool is used here. So this is some technical idea of uh, calorimeter and very simple article. Now the next one is latent heat. Now what is the latent heat? In simple words, during the change of the state, heat energy absorbed or given out by the body without change its temperature. And this already we studied in our previous syllabus, how this happens. And the example is ice. When heat is supplied to the ice, it is in solid form, it convert into liquid, again means water, again this water will start to boil and it convert into vapors. So there is change in state of the matter is there, means in solid form the matter is there, it converts into liquid. But during the change in state, what heat energy is absorbed or evolved, absorbed by the body or given out of the body without change in temperature of the body, this heat is known as latent heat. And in our syllabus the definition, latent heat of the substance is the quantity of heat required to change the state of unit mass of the substance without changing its temperature. So just I explain the latent heat, and the definition of the latent heat is there. Here in our syllabus, two types of the heat uh, we have to consider. One is uh, okay. Here is the equation for the latent heat. It is m into L. M is the mass of the substance, and L is the latent heat. Now, latent heat of fusion, and the definition is the quantity of heat required to convert unit mass of substance from its solid state to liquid state at its melting point without any change in its temperature is called latent heat of fusion. Just I explained what is latent heat, and two types of the heats we have to learn. Fusion means when the substance is from solid state to liquid state. During this change in state, uh, the melting point is there, uh, but during the change of the state there is no increase in temperature or decrease in temperature of the body. Temperature remains same, okay, during the change of the state. So this is the latent heat when the substance change from solid to liquid. Okay, then SI unit of the latent heat of fusion is joules per kilogram, and CGS is calories per uh, gram. Okay, uh, joules here erg per gram should be there. Okay, Now the next heat is the latent heat of vaporization. Now same definition is there, the quantity of heat required to convert unit mass of substance from liquid state to vapor state. Only these words are changed, all other words will be same at its boiling point. This line and these two words will be changed, without all other words will be remain same. Even the units will be same for the latent heat of vaporization. So heat transfer, and we know that there are three modes of transfer, heat transfer: uh, conduction, convection, and radiation. In today's lecture, we'll try to consider the uh, mode of transfer of heat, that is conduction, and next lecture we'll try to learn uh, convection and radiation. Okay, so we'll start to discuss the uh, mode of transfer of heat, that is conduction. Conduction is the process by which heat flows from one hot end to the cold end of a solid body without actual migration of the particles of the body. Even you can say the conduction is the mode of the transfer of heat from higher temperature end to the lower temperature end without actual migration of the particles of the body. Anyway, you can state the statement for the conduction. Okay, now what is it? Heat passes through the solid by conduction. Only in solids the heat is passes by this process, that is conduction. uh, One end of the rod is heated. Molecules near the hot end receive the thermal energy, and it will be start oscillate. Amplitude of the oscillation will be uh, goes on increasing, and during this oscillations they collide with the neighboring particles, so that the neighboring particles will be receive the heat and they will start to vibrate about their main position. Amplitude is increases, again these molecules collide to the neighboring molecules, so that molecule to molecule, particle to particle, the heat is transferred, and uh, uh, there is the heat is transferred in the solid. So this process is explained over here. Just I said, uh, the molecules of the solid receives the heat from the neighboring molecules. Oscillations increases, that is amplitude increases, they collide with the neighboring molecules. Like that, molecules to molecule, particle to particle, heat is transferred, and heat from higher temperature end reaches to the lower temperature end. So this is the process to transfer the heat continuous till the cold end. Okay. Now conduction is the process. Here we have to consider the good conductors and bad conductors. The substance which conduct heat easily are called good conductors of heat. All the metals are the good conductors of heat: steel, silver, aluminum, etc. uh, Insulators, the substance which do not conduct heat easily, are called insulators or bad conductors of heat. uh, Here glass, wood, air, paper, etc. I think uh, these articles we try to study in our second video. Okay, little bit complicated, different articles are here, but a simple article we try to learn in this video. So students will stop here, and next time we'll discuss uh, convection, radiation, and Newton's law of cooling in the next video. So we'll stop here. Thank you.